All right, hello, Physics 121 people. I got this question sent to me. It's about, again, Newton's second law, and it's about an object. I think this one's on a flat surface, but I want to run this one again, and I'm going to go through the same process of most of my videos on this, is that there are 4 steps you want to follow. Step 1, get a good physical picture of what's going on. And if that's done well, it makes the next step a little easier, which is to get a free body diagram. And if that's done well, that really helps going to the next step, step 3, which is to write out a system of equations. And then step 4 is to solve those. And so I'm going to run through those and encourage you to kind of memorize those 4 steps and practice them as you do the problems, and then you'll be very strong at doing this. They take a while, I must admit, but those 4 steps are really nice. Okay, so let's just read this problem together, and again, start with number 1, good physical picture of what's going on. So we got a box, okay, a box with a mass of 4 kilograms, and it is on a table that has a kinetic friction of 0.4. Now, the sentence ends there, so I probably need to keep reading, but my first, unless I read otherwise, is to imply that a table is level. So I'm going to draw a little table. Maybe I'll put some legs on the table, but I'm going to just start with a level surface. And then on that, I'm going to put this 4 kilogram block. Oops, maybe I should do 4 kilograms up there. Give myself a little more space. And there it is sitting on top. Give myself a little bit of gap, so maybe I can draw something there. But that's the first sentence. Notice they did give me a coefficient of friction, so I think this will be moving. Let's see if they say anything about static friction. It says, it is pulled by a rope with a tension of 36 newtons at an angle of 30 degrees above the horizontal. Okay, so the rope might be tied like this and be angled up. And so I'll just make a little dotted line for horizontal. But there is the 30 degrees. And the pull, they even tell me how much that is. That's a pull of 36 newtons. Okay. And notice above, 30 degrees above. Okay. And it looks like the question says, what is the acceleration of the box along the table? So that question kind of indirectly implies that it moves along the table and has an acceleration along the table. So it looks like this here is going to overcome the static friction, then start to slide, and so the static friction will turn into kinetic friction, and it will slide along. And so I think I just did step number 1. Do we got a good physical picture of what's going on in your mind? Do you see this block, and it slides along? And as it slides along, of course, it's being pulled because of this thing here. But as it is being opposed, if you will, by some rubbing that's going on there. So maybe I'll put a bunch of squiggle marks in here to say, okay, so there's rubbing here going on. All right, so that leads to free body diagram. All right, so here is my free body diagram. And what we mean by a free body diagram is draw just the object in question, and then all the forces involved, but only drawing the item in question means you can focus on that item and you can focus on the forces and you don't get lost. Is there a table? Is there an earth? Is there a rope? Who's pulling on it? And all these other questions that can come into play and make it confusing. The only thing that really matters is the forces on that block. And it doesn't matter what kind they are. That is, if they come from gravity, or if they come from tension, or if they come from a spring, or if they, come from magnets. None of that really matters. So that's why we like to say, look, don't really draw anything else. All right, so let me draw those forces. And I like to say that the forces would be the force of gravity plus everything touching it. So I'll start with the force of gravity. So pulling down. Oh, and I did the last one in green. So maybe I'll do the forces in green. Okay, so mg is pulling straight down, gravity's pulling down, so there's the first one, and everything touching it. Well, the table's surface is touching it, and technically that's kind of one force, but we like to take that one force and break it apart into its component. That is, how much is the table pushing perpendicular to itself, and how much is the table pushing or rubbing, if you will, tangential to the motion. In the last little video, I kind of maybe said, oh, that would be just one force off at an angle. So I'll do a different color and maybe even cross it out, because you might think that that's a third force. But these two together are the components that are along the surface and then perpendicular to the surface. All right, so let's just recap here. So I've got gravity and everything touching it, so the table's touching it. There is another item touching it, so this problem might be a little harder than the last one, because there's two things touching it. However, it's not at an incline, so maybe it's easier, but nonetheless, I'm going to say then that there is a force, and that one is directly given with a magnitude of 36 newtons and an angle of 30 degrees. And so I think that completes step 2. Did I draw the object and all the forces? Yeah, I did gravity and everything touching it. There's only two things touching it. These are the components of the one coming from the table, and then this is the one from the table, which I probably will have to break down into components also. I'll talk about that in a moment. And then, of course, gravity. I already said that. So I think I've done the first two steps here. I haven't got to the math yet. That's coming. This is step 3, write out the equations, and step 4 is solve the equation. But what I've done is I've got a good physical picture of what's going on, which kind of understanding it really helped me figure out what forces there are. So the free body diagram. And of course, it's this free body diagram with the forces that really helps out in this step, step 3, to write out the equation. And this is the place where I always say, okay, now writing out the equation means you need a grid. You need to know what is x components and what is y components. And what do we pick for the grid? And what I like to always say in these problems is pick one of your axes, the direction of the acceleration, if you know it. And so this problem is implying that it slides across the surface of the table. This is where coming back to step 1 is really helpful. And so it's going to be accelerating along the table. So the tug upward doesn't make it go up. It probably does loosen the interaction down here, and so loosens up the friction that it would have had. Okay, so we can look in the math there, but it doesn't actually go that way. So I'm going to set up a grid in the traditional fashion where x is horizontal and y is vertical. And again, I'm not setting up this grid because it's traditional. I'm setting up this grid because when I do this, the x-axis is the direction of the acceleration. And so when I get into step 3 here and I say, okay, let's add up things for the x-axis and add up things for the y-axis, and that first step says add up all the forces in the x direction and set it equal to ma. And if I do it for the y also, add up all the forces in the y direction and set it equal to ma. The a's that we're talking about are the a's which are the acceleration in their respective directions, the x direction and the y direction. So this is why I always say here in step 3, when you start writing out your equations and you set up your grid, if you set up your grid so that one of the axes, usually the x, is along the direction of the acceleration, this next step I can just say ma. There's no point in calling it an x component or a y component. This is the full acceleration, and that's usually what we're looking for. You see, if you had components of the acceleration, then to get the total acceleration, you'd have to get these separately and individually, and then do an ax squared plus an ay squared. So that could be the real advantage. Plus, over here then, you can say it has 0 acceleration. And as you'll see, it's really nice to have equations that are equal to 0. All right, well, continuing to work on step number 3. let's add up all the forces in the x direction. So the force of gravity is all in the y direction, so I won't put it here. It will go over here a little bit later. Force of friction. So all the friction is in the negative x direction. So there's no sine or cosine to put in there, but it's the negative direction. So minus the magnitude. The normal force is all y direction, so nothing would go here. It'll go over here. And maybe the harder one is right here, where we're going to have to look at this in terms of its components. That is, this 36 would have so much along the x-axis and so much along the y-axis. And to get the part along the x-axis, which I would want here, I would want this piece, which is adjacent to the 30 degrees. So this would then be a plus 36 cosine of 30 degrees. And so there would be maybe the ending point of step 3. I still got to solve it and go on to step 4. I'll pause so that I can finish step 3 for the y direction. Sometimes that's better. Sometimes it's better to, keep going on and solve this. But I think I'm going to jump over here before I try to solve this and just say, okay, let's continue to work on this step 3, which is to write out these equations. All right, so let's go to the y direction. So going around the same forces, there's the force of gravity, which is all in the y direction and in the negative. So it's negative mg. The other force here, the force of friction, is nothing in the y direction. The normal force is all in the vertical direction. And it looks like this has a small component of the vertical direction, so it's positive, and it would be the 36, and it would be the opposite, so it would be sine of 30 degrees here. Okay? Now that I've written out, I would say I've completed step 3. I've written out the equations based upon this grid and Newton's second law, and now I can begin to solve it. And we're trying to find the acceleration. So you probably would be tempted to do this equation first, however. The force of friction is the coefficient times the normal. So you can't really go anywhere until you know the normal. Now we do know the coefficient of friction and we do know the mass, which we're looking for the A. So if I just knew that normal, I could put it into here and get the A. So that's why I'm going to have to really solve this one first. So this would say the normal force is, and I'll move the negative mg to the other side so it becomes positive, and then minus the 36 times the sine of 30 degrees, which of course, these two together is 18, since the sine of 30 degrees is 1/2. And in fact, this might be a good time to pause and maybe make sure we are following the math, not just in terms of doing an equation, but what I like to say, we're reading the math. And as we read this math here, we begin to say that the normal force is the weight minus a little bit. Now, let me say 2 things about that. The first one is, again, notice that the normal force does not always equal mg. There, for some reason, is just a human tendency for students to go, oh, normal force, that's the upward, and gravity's pulling it down. And, well, no, there's so many other things going on that other things can be pulling it up. And that's what we see. I think in that logic, what you're really trying to say is what pulls it down, mg, has to equal what pulls it up. And that is true. You can see that if I just moved mg to this side, I would have mg equal to the 2 things that are pulling it up. So the normal force and this little component are pulling it up. They have to equal mg. That's true. And that's why the normal force is a little bit less than mg. It's mg minus that little bit pulling up. Because again, these 2 pulling up have to equal the mg pulling down. Okay, so now I can get this normal force because the mass is the 4, and when we multiply it by 9.8, we get the 39.2. And then when we subtract off the 18, we get a 21.2 newtons. Now we can use that back onto the x-axis. Okay, so minus, and let's see, for this problem, what was the coefficient is 0.4. Okay, so 0.4 times this 21.2 plus this 36 cosine of 30 equals 4a. All right, so why don't I do the negative 0.4 times, looks like the last answer, plus the 36 times cosine of 30 degrees, and I'll just hit enter. So that makes the net force at 22.7-ish. And if I divide that by the 4, and I get a 5.67 meters per second squared. Yay! And so that should be the acceleration. All right. Hope those 4 steps in particular, because all of this chapter, you can do all of these if you kind of follow those 4 steps. All right. Take care.